All right, we're going to start, like I said, chapter 4, which is on Laplace transforms. We're going to start with complex numbers, complex variables, and complex functions. This is just a quick review of this stuff. Well, it's a couple pages, so it's not really that quick. And then we'll go on to looking at the Laplace transform. You should have been exposed to Laplace transform in DiffQ, and we're going to build upon that in this class. So first we're going to start off with a complex number. So just as a reminder, a complex number, we'll say z here, has both a real and an imaginary part, where x is our real part, y here is the imaginary part, j here is the imaginary constant. We can also plot a complex number on the complex plane, as shown to the left here. Basically, we have real as our x-axis, imaginary numbers as our y-axis, and then our complex numbers live somewhere in that plane. We can express the magnitude of a complex number as the Euclidean norm of the two components. So the magnitude of z is equal to x squared plus y squared. Then you can also express a phase as, we'll just say theta here is equal to the tangent, or the inverse tangent of y over x. So on that plot, we can see theta is already drawn there, but this distance that I'm drawing in red here, that's our magnitude of z. All right, so we can express a complex number in either rectangular form or in polar form. There are two ways to express it in rectangular form. The first is exactly what we've just seen. That is z is equal to x plus jy. That is one way to do it. Another way is we can say that z is equal to the magnitude of z times the quantity cosine of theta plus j sine theta. And those two are our rectangular form. We can also write it in a polar form. We can say that z is equal to the magnitude of z times e raised to the j theta. And sometimes you'll see it written as z is equal to the magnitude of z times the angle theta. And these are our polar forms. All right, we can also define what we call the complex conjugate of z, and that is simply equal to, and we're going to use a overbar to indicate a complex conjugate. So z over bar is equal to x minus j times y, which is then equal to the magnitude of z times e to the minus j theta. Or in the other rectangular form, we'll write the magnitude of z times the quantity of cosine theta minus j sine theta. So embedded in this polar and rectangular forms is what is known as Euler's theorem. And Euler's theorem is that e to the j theta is equal to the cosine of theta plus j sine theta, and then e to the minus j theta. That is equal to cosine of theta minus j sine theta. You can combine these two equations, and doing so results in the following, that the cosine of theta is equal to the fraction e to the j theta plus e to the minus j theta, that divided by 2, and then the sine of theta is equal to the fraction e to the j theta minus e to the minus j theta, and then that divided by 2j. Okay, we're going to go over some arithmetic with complex numbers. Then we'll go on to complex functions, and then from there we'll be able to go into the Laplace transform. Okay, so we can just add two complex numbers by adding their components together. So if we have z equals x plus jy and w equals u plus jv, we can just add these together as z plus w is equal to x plus jy plus u plus jv equal to x plus u plus j times y plus v. And subtraction works similarly as well. For multiplication, what we do depends on what we are multiplying. We are just multiplying some scalar value a by a complex number z. Then we're just going to distribute that value a. So if we have a multiplied by z, we'll just distribute this and we'll get ax plus jay. If we multiply two complex numbers, we've got to do some more work. If we have z times w, this is equal to x plus jy times u plus jv. We have to expand this. We're going to get xu plus jyu plus jxv plus j squared y times v, and this will then be equal to xu minus yv plus j times xv plus yu. This should be xu minus yv in polar form. It's much easier to multiply things together. We'll have z times w. In this case, we just multiply the two magnitudes, and then in the exponential, we'll add their phases together. If we multiply by the imaginary constant, this is equivalent to rotating by 90 degrees counterclockwise, such that if we have j times z So it'll be equal to, well, j times x plus jy is equal to minus y plus jx. And then this is then equal to the magnitude of z times e to the j theta plus pi over 2, or plus 90 degrees if you're working in degrees. So multiplying by imaginary constant rotates our complex number in the complex plane by 90 degrees. So we can do division as well. It's generally easier in polar form, though you can do it in rectangular form. It's just much easier in polar form. So if we have z divided by w, this will just be equal to the magnitude z times e to the j theta divided by the magnitude of w times e to the j phi. And then that just becomes the magnitude of z divided by the magnitude of w times e to the j theta minus phi. If we do division in rectangular form, we are going to have to multiply by a complex conjugate. I'll show what that looks like. So if we do z over w, this will be equal to the quantity x plus jy divided by u plus jv. We now, in order to compute this division, we've got to multiply and divide by the complex conjugate of the denominator. So we're going to get, in the numerator, we'll get x plus jy multiplied by u minus jv, and in the denominator we'll get u plus jv multiplied by u minus jv. And then we can go and compute what this ends up being, and it simply ends up being xu plus yv divided by u squared plus v squared plus j times the fraction yu minus xv divided by u squared plus v squared. And well, that's the answer. So as you can see, division is just easier, quite straightforward, easier in polar form. If we divide by the imaginary constant, that's equivalent to rotating clockwise by 90 degrees. So multiplication by j is rotation by 90 degrees counterclockwise. Division is rotation in the opposite direction. So we just do z divided by j. This is equal to, in polar form, z times e to the j theta minus pi over 2. Rectangular form, we're going to have to multiply by, well, not the complex conjugate, but just j over j. So we'll get, this is x plus jy, all of that divided by j. From here, we just multiply by j over j. So we'll get j times j in the denominator. And then x plus jy times j in the numerator. And this will result in y minus jx. Okay, for powers and roots, we're just going to do that in polar form. if we raise z to some constant n, this will be equal to the magnitude of z times e to the j theta raised to the n, and then this becomes the magnitude of z raised to the nth power times e to the jn theta. If we take a root, the nth root of z, this is then magnitude of z times e to the j theta, 1 over n raised to the 1 over n, and then we'll just bring that on in. We'll get z raised to the 1 over n times e to the j theta divided by n. And you can do that in rectangular form, but it's just much easier in polar form. Okay, we can now talk about complex functions. So complex function f of s has both a real and imaginary part, and we can simply just say f of s is equal to some real part f sub x plus complex part j times f sub y. And the variable, or the independent variable s itself, can also be complex. So a complex function is a function that will have both real and imaginary parts. And we also consider cases where the independent variable is complex as well. All right, so most of the functions that we are going to encounter here are going to have the following form. F of s will be equal to, it's going to be some fraction where we have some constant k times s plus z1 times s plus z2, all of that multiplied up to s plus zm, and then divided by s plus p1, s plus p2, up to s plus pn. And when we start dealing with the Laplace transform stuff, we will see where these show up. When we start applying the Laplace transform to solve differential equations or just dynamical systems in general, we'll start to see this pop up. Okay, so the points where this function f of s is equal to 0, these are called the zeros. And those are when s is equal to minus z1, s is equal to minus z2, all the way up to s is equal to minus zm. So all of those are called the zeros. In the denominator, we'll see that if the denominator ever goes to 0, then this function f of s is going to blow up and go to infinity. And we call those poles. And that is when s is equal to minus p1, s is equal to minus p2, or s is up to s equals minus pn. Again, are the poles. So I think when we did steady state vibrations and we looked at resonance, we found that the system or the response would blow up whenever the forcing was equal to the natural frequency omega n. It's a similar kind of concept here. In this case, the poles are, well, the natural frequencies are equivalent to poles. In this kind of context. Okay. Any questions? All right, then we are ready to go on to the Laplace transform. And so in general, we're going to be considering the Laplace transform method. This is an operational method that we're going to use to solve linear time invariant differential equations. So in the first part of this course, we looked at how do we solve them from a vibrational perspective. For most of the rest of the class, we're going to be using Laplace transforms and converting into a complex domain and solving them there. So the main advantage of this is that the differentiation of a time function in the time domain corresponds to the multiplication of the transform of that function by the complex variable s. And then as a result, when you take the Laplace transform of a differential equation, you get back an algebraic equation that you can then go and solve for the transform. And then you can take an inverse transform to then compute the solution to that differential equation. We'll have two options for finding the solution, either using transform tables or using what's known as partial expansion technique. And we'll go over those as well. Another advantage is that these initial conditions are automatically taken care of, and you also get both the homogeneous and the particular solution at the same time. They're obtained simultaneously. Okay, so we're going to define our Laplace transform. We're going to write it as a script L acting on some function f of t. So L is what is known as an operator, and it acts on a function. And this is going to be equal to f of s. So capital F of s is the Laplace transform of that time function f of t. And then this is equal to the integral from 0 to infinity of e to the minus st times f of t dt. And then we'll define the inverse Laplace transform, L inverse acting on f of s as being equal to f of t. We're not going to go into the integral form of the inverse Laplace transform, primarily because we will either just use a table or we'll use simplified forms where we'll already know how to do the inverse. All right, we're going to cover the existence of the Laplace transform, specifically like when does it exist, when does it not exist, which then tells you when can you use it, when can you not use it. And then we'll look at what happens when we apply a Laplace transform to several common functions. Okay, so the Laplace transform of a function f of t exists if the Laplace integral converges. That's that integral from 0 to infinity of e to the minus st times f of t. That integral is going to converge if our time function is piecewise continuous and every finite interval in the range of t greater than 0, and if f of t is of what's known as exponential order. And we're going to talk more about that in a moment. The key thing here is that we're considering what happens after t equals 0. We don't really care what happens before that point. Which works well because generally when we're looking at differential equations, we're defining what the initial conditions were, not what happened in the far past. Okay, so a function f of t is of exponential order if a real and positive constant sigma exists such that the function e to the minus sigma t times the magnitude f of t, if this goes to 0 as t goes to infinity. So in the limit as this function approaches 0, if the limit of this function e to the minus sigma t times the magnitude of f of t, if this approaches 0 for sigma being greater than some other constant sigma sub c, and the limit approaches infinity for less than sigma sub c, then we'll call this constant sigma sub c the abscissa of convergence. And we're going to go look at what that is for a few different functions. So For functions like t, sine of omega t, and t times the sine of omega t, the abscissa convergence is 0. For functions like e to the minus ct, t times e to the minus ct, and then the damped sinusoidal, then the abscissa convergence is minus c. Meaning that we can apply the Laplace transform to these functions because an abscissa of convergence does exist. Okay. So functions that increase faster than an exponential function do not have an abscissa convergence, and that means they do not have a Laplace transform, meaning that you cannot compute the Laplace transform. So things like e raised to t squared or t times e to the t squared, things like that do not have Laplace transforms. You cannot apply this technique to those functions. However, there is kind of an exception to this, and that is if you define a piecewise function that has one of these functions for some limited duration, then you can compute the Laplace transform of that. So for example, if we define f of t being equal to a piecewise function, let's say 0 for t less than 0, e to the t squared for 0 less than or equal to t, less than or equal to some big T, and t here needs to be something that's less than infinity. And then after little t reaches big T, we'll have 0, and then this is for t, little t greater than big T. This is a signal that you could physically generate if you had like a signal generator, and as a result, it does have a Laplace transform. And that's specifically because we've forced this function that increases faster than the exponential function, we forced it to have a finite duration. And as a result, you can take the Laplace transform of this. So signals that can be physically generated, meaning that you can go into a lab and actually generate this through a signal generator, or the signals that you measure from some system. These things are, well, one, they're real physical signals, and as a result, they will always have a Laplace transform. So any signal that you can physically generate will always have a Laplace transform. Okay, we're going to take just a brief look at how to compute Laplace transform of the addition of two functions. Then we'll take a look at the exponential function, step function, ramp function, and a few other functions from there. So we have two functions, f1 of t and f2 of t. Then the Laplace transform of their summation will be the script L acting on f1 of t plus f2 of t. Oops. We can split this up and apply the Laplace transform to each of those separately. And as a result, this means that if you have some complex function composed of many different parts, you can just take the Laplace transform of each component separately and then add that up together. And this is because the Laplace transform is what's known as a linear operator.
Kind of confused what a linear operator is. Is that just because you can split the two up? Is that what makes it a linear operator?
No, so it's a linear operator, and as a result of it being a linear operator, you can do the superposition. So we won't go into operator theory, but things like differentiation is a linear operator, meaning that it's something that operates on functions. Integrals are linear operators. Summations are linear operators. So you can switch if you have a summation of, if you're summing up a bunch of integrals, you can switch the order of the integration in the summations. That's really what this means here. Yeah. So like I said, yeah, integrals are linear operators, and this is an integral transform method, and therefore it's a linear operator. When you get into higher math, particularly a little bit above a partial differential equations class, like maybe a second partial differential equation class, that's when you will cover what true operator theory is. and then you can study properties of these operators. The key thing is that this is linear, and that means that things like superposition hold for us. And I think consequently that may mean that we will not be able to apply Laplace transforms to nonlinear differential equations. Okay, moving on, we're just going to take a look at what happens if you have an exponential function. In this case, we're going to be defining a piecewise exponential function. So f of t here is equal to 0 for t less than 0, and then a e to the minus alpha t for t greater or equal to 0. We're going to see this a lot where we are forcing, where our function needs to be 0 for t less than 0. And so a and alpha here are constants. We can go and compute then the Laplace transform. Laplace transform applied to a e to the minus alpha t. So this is equal to the integral from 0 to infinity, a e to the minus alpha t times e to the minus st dt. This is equal to, we can pull out the a because that's just a constant, integral from 0 to infinity of e to the minus alpha plus s, all that times t dt. And if you go and you compute this integral, you'll find that it ends up becoming a divided by s plus alpha. And of course, in doing this, we have integrated this and then taken a limit as s goes to infinity. We've also assumed here that the real part of s is greater than minus alpha so that we can get convergence in an integral. However, that's not really that big of a deal for what we're dealing with here. Yeah, so the key thing here is that the Laplace transform is of the Laplace transform f of s of any Laplace transformable function is going to be valid in our entire complex domain except at the poles of f of s. And in equation 28, minus alpha is the pole for that system. So we obviously cannot compute our function, Laplace function, goes to infinity when s is equal to minus alpha, and hence why it's no longer valid at that point. Okay. So just as a reminder, this is the pole for that transform. When we start dealing with, probably not in this class, but when you take controls, you'll start dealing with what the poles and the zeros are of your control system, and it's exactly this. All right, we'll take a look at what's known as the step function. In this case, we have f of t equal to 0 for t less than 0, and then some constant a for t greater than or equal to 0. If we were to plot this function, it is 0 up until time 0, and then suddenly it becomes that constant a. Hence why it's called a step, because there's just a step in it. So Laplace transform of the constant a, we'll just say, is equal to the integral from 0 to infinity of a e to the minus st dt, such that this is equal to a divided by s, such that the pole in this case is s equals 0. Okay, now that we've seen the step function, we can now define what we call the unit step, or the Heaviside function is another name for it. So the unit step, we'll use u of t is equal to, or if you want to call it the Heaviside, we'll use a capital H of t, and this is equal to 0 for t less than 0, and then 1 for t greater than or equal to 0. And then sometimes, depending on what you're dealing with, you may define the step function or unit step at 0 to be equal to 1/2. Other times you may say it's undefined at 0. Generally, I just say it's 1 at 0. But it does sometimes make a difference. In this class, we're just going to say it's 1 at 0 for simplicity. So we can also shift the step function in time. And in that case, we will say that u of t minus t0 is equal to 0 for t less than t0 and 1 for t greater than or equal to t0. So I'm also going to graph what each of these looks like. So the unit step is 0 for t less than 0, 1 for t greater than 0. When we shift it in time, it's going to be 0 up until that shifted time. And then after that shifted time, it's going to be 1 for all time. So what's cool about the unit step function is that it's really a building block for creating piecewise functions. And I think that we'll see this later when we look at the pulse function. But it's a building block that allows you to build piecewise functions as a single expression. All right, we're going to look at the ramp function, which is actually the integral of the step function. F of t is equal to 0 for t less than 0, and then a t for t greater than or equal to 0. Where a here is a constant. We'll go and plot this as well. So this function is going to be 0 up until time t, and then it's just going to grow with the slope of a. And this one does not have a discontinuity in it, unlike the step function. Okay, so the Laplace transform of AT is equal to integral, or a times the integral from 0 to infinity of t e to the minus st dt. And we got to evaluate this using integration by parts. So we'll do the integral from a to b, or this is the general formula for integration by parts, of u dv is equal to u times v valued from a to b minus integral from a to b v du. That's just our formula for integration by parts, just as a reminder. In this case, we're going to say u is t, dv is e to the minus st dt, and then from there, we will show that this Laplace transform of at is equal to, pull out this a, we're going to get t times e to the minus s, t divided by s, evaluated from 0 to infinity, minus the integral from 0 to infinity of e to the minus st over minus s. There's also a minus sign over here in that first portion. Then dt. And this ends up being equal to a over s times the integral from 0 to infinity of e to the minus st dt. And so it turns out that this is a over s squared. So the Laplace transform of at is equal to a divided by s squared. Okay, we'll now consider a sinusoidal function, ft, again 0 for t less than 0, and in this case a times the sine of omega t greater than or equal to 0. And again, a and omega here are constants. In order to compute the Laplace transform of the sine of omega t, we're going to end up expanding it into the complex form. So I'll just write that here. Sine of omega t is equal to 1 over 2j times e to the j omega t minus e to the j omega t. That should be e to the minus j omega t. Okay, so then our Laplace transform of a sine omega t is going to be equal to, we could pull out an a over 2j out of our integral, then the integral from 0 to infinity of the quantity e to the j omega t minus e to the minus j omega t. That all multiplied by minus e, or e raised to the minus t, st dt. This will end up being equal to a over 2j times 1 over s minus j omega minus 1 over s plus j omega. Then you can go and compute this out, and you'll find that the Laplace transform of a sine omega t is equal to a omega divided by s squared plus omega squared. We can do the same thing for cosine, and then if you carry that out, you'll find that the Laplace transform of b cosine omega t is equal to b times s divided by s squared plus omega squared. Okay, we're going to talk about what's just a function that's been translated in time, shown here. I need to make a small correction here. So in this case, we'll have some function f of t minus alpha multiplied by a translated unit step, shown here, where alpha is, well, greater than or 0. Below, I've provided the plots for what this function would look like. This 1 of t here, this is our unit step. The book likes to use 1 as a function of time, and I really don't like that because it just looks like multiplication. That should be u of t minus alpha. So anyway, once we are multiplying by this translated unit step, you can see how the function originally it started at 0, now it starts at some time alpha. So in this case, the Laplace transform of f of t minus alpha times u of t minus alpha, this is equal to e to the minus alpha s times f of s, where f of s is the Laplace transform of the untranslated function. All right, so we're going to move on to what is known as the pulse function. This pulse function is a finite duration pulse with some finite amplitude. We'll see why that matters in a moment. It's going to be defined as f of t is equal to 0 when t is less than 0. A divided by t0 for 0 less than equal to t, less than or equal to t0, and then 0 for t greater than t0. And so now I have this three-part piecewise function. We can also express it in terms of using the unit step. And say f of t here is equal to a divided by t0, that's our amplitude, times the unit step of t minus the unit step of t minus t0. And so in this case, first unit step becomes 1 at time t equals 0, and the second unit step becomes 1 at time t equals t0, and then they cancel each other out at that point. So as a result, we can use the unit step function to build piecewise functions. And yeah, like I said, you can use it to construct any piecewise function. So in this case, the Laplace transform L of f of t is going to be equal to a divided by t0 is just some constant. So we can pull that out, times the quantity Laplace transform acting on this u of t minus Laplace transform acting on the translated step function u of t minus t sub 0. And we'll find that this is equal to a divided by t0s times 1, the quantity 1 minus e to the minus t0s. Okay, we take a look now at our impulse function. So the impulse function is a special case of the pulse function. It is defined as f of t is 0 for t less than 0, and then it's going to be the limit as t goes to 0, as t sub 0 goes to 0 for a divided by t0. This is true for t greater than 0, less than t0, and then 0 for t greater than t0. And the key idea here is that the area underneath this impulse function is equal to a, and this is true even as this t sub 0 goes to 0. We're going to talk about the Dirac delta, or the unit impulse function, and then we'll go back to this impulse function. So we're going to represent this unit impulse as a delta of t, or if it's translated, delta of t minus alpha. And in this case, this delta of t is defined to be 0 for t not equal to 0 and infinity for t equal to 0, which is not really a true function because a function cannot be equal to infinity. But really what this means is that the truth is that this Dirac delta is actually defined based on its integral. So if we take the integral from minus infinity to infinity of delta t times dt, this is equal to 1. That is our definition of the Dirac delta. And then from here you can go and find the impulse function. The impulse function would be that constant a multiplied by our Dirac delta. So Dirac delta is really used to represent impulses. Very, very sudden changes in an input to a system that are very short duration. Things like impact between particles is an impulse type problem as well. It can be represented by Dirac deltas. The nice thing about Dirac deltas is that when they're multiplied by some function, if you take the integral from minus infinity to infinity for the quantity g of t times delta of t dt, this is then becomes equal to g of 0. And for a time translated one, the integral from minus infinity to infinity of g of t times delta of t minus, let's say a here, dt, this will be equal to g of a. So then our impulse function can then be written in terms of our Dirac delta. We can say here that f of t is equal to that constant a times delta of t. And then from here we can go and compute the Laplace transform. Laplace transform of a delta t. We can pull out the a, so then we're going to get just the Laplace transform of the Dirac delta. And the nice thing about this is that this is the Laplace transform of the Dirac delta is just 1. And so we'll get that this is equal to a. Okay, with that, we're going to take a 2-minute break, and then we'll come back and we will probably get through initial value theorem. All right, so if f of t includes impulse at time t equals 0, then we need to specify whether we're going to, what the lower limit of our Laplace transform is, whether we'll say it's 0 minus or 0 plus. 0 minus means that we're including that impulse function in our Laplace transform. 0 plus means that we're excluding it. 0 plus is just a little bit after, 0 minus is a little bit before 0, infinitesimally small, a little before. And as a result, the Laplace transform is going to just differ based on that choice. So then for 0 minus, we can specify with the Laplace symbol, a little script L with the subscript of a minus sign. For 0 plus, we'll have a subscript of a plus. This is going to show up when we look at this differentiation theorem, which is where we're going right now. So the Laplace transform of a derivative of some function. So we take Laplace transform of a derivative d over dt times f of t. This is equal to s times f of s minus f0, where f0 is the initial value of that function at time t equals 0. And then if we have two different initial conditions, or two different, slightly different before and slightly different after, for example, if there was an impact in the system, there would be a sudden change in velocity of the components. As a result of that, you would either need to be specifying before or after that impact. In that case, we will end up using for just before, we'll have script L with a subscript of the minus sign, d of dt acting on f of t. This is equal to s times f of s minus f at 0 minus. And then if we do the opposite, or just after, we'll get the Laplace transform of d over dt f of t equal to s f of s minus f of 0 plus. For the second derivative, we'll take the Laplace transform of d squared over dt squared of f of t, and this is equal to s squared times f of s minus s times f of 0 minus f dot of 0. So for second derivative, we need to include the initial condition for the function itself, as well as the initial condition for its first derivative. And you can extend this out to n derivatives. And so the Laplace transform of the nth derivative, dn over dt to the n of f of t, this will be equal to s to the n times f of s minus s to the n minus 1 times f of 0 minus s to the n minus 2 times f dot of 0 minus dot 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 minus d to the n minus 1 f dt to the n minus 1, that evaluated at t equals 0. Okay, we're going to go through final value theorem, initial value theorem, and then we're also going to do integration theorem, and then we'll be done. So the final value theorem allows us to relate steady state behavior of that function f of t to the behavior of s times f of s in the neighborhood of s equals 0. This theorem only applies if the limit of f of t as t goes to infinity exists. When that's true, we can then find the final value, or the limit as t goes to infinity, of f of t. This is equal to the limit as s goes to 0 of s times f of s. Then the initial value theorem is the counterpart to that. It allows us to find what happened at just slightly before 0, not exactly at 0, but a little bit before. And in this case, we can write that f of 0 plus is equal to the limit as s goes to infinity of s times f of s. All right, integration theorem. So if f of t is of exponential order, then the Laplace transform of its integral will exist, and we can define that as Laplace transform. In this case, we're going to do an indefinite integral of f of t dt. This is equal to f of s divided by s plus f inverse 0 divided by s, where this f to the minus 1 is the integral. It's not the inverse of the function, it is just the integral form. Evaluated t equals 0. That's for an indefinite integral. If we have a definite integral, then the Laplace transform of the integral from 0 to t of f of t dt, this is equal to f of s divided by s. And so we lose that additional term. Okay, so I've included, actually it was a question, yeah.
I was just going to ask the definite integral, would you need a plus c?
In the indefinite one, that is taken care of through here. Yeah. Yeah, I get what you're saying. This is effectively that constant. And the reason why we don't have it here is, well, because it's a definite. All right, so I included the 3 tables from the book in your notes, so you have a copy of them. And then on Wednesday, we'll start 4.3, which is on the inverse Laplace transform and applying that to solve equations.